A little late to the party. Sorry about that. Everybody say hi.
Hi.
What we're doing is solving this problem right here, and we just took a couple of minutes to translate this problem from English into math. So we have two positive numbers. We call them x and y, and we say that they are positive. Their sum is 20, so x plus y is 20. And their product is a maximum, so we call that product p, and we write it as x times y. And now we're trying to maximize this guy, and the only obstacle that I have really is that it's a function of two variables, right? So we experienced this yesterday. So the way we handle that is by substituting one of our variables away, and that's where our constraint comes in handy. The constraint allows me now to solve what is x equal to? 20 minus y, and therefore I can plug that right in there, and I get 20 minus y times y is equal to the product that I am looking for to maximize. Yes, sir?
What is the interval for x again?
Good. Well, actually, I'm interested in the interval for y, because and that interval is going to be 0 to 20. There's my domain, because y has to be positive, and also y cannot be bigger than 20 because that would force x to be negative.
Does that mean that you're including 0 though?
I am, only because, you're right, the domain is technically the open, right? But I'm including those endpoints because my method for finding maxes requires the use of the endpoints. So I'm cheating a little bit.
But it wouldn't be a maximum because 0 times 20 is 0.
Right. You're exactly right. We're not going to find the max at the endpoints today. I mean, we'll try, but it will not be. How are we doing so far? Does this make sense? Okay. So now having done this, I've got p is equal to, I think we should simplify 20y minus y squared. And now we're ready for critical points and endpoints. Find the critical points. Easy enough. dt dy equals 20 minus 2y. Set that equal to 0. And I get one critical point, y is equal to 10. And now I'm ready to evaluate my product at the critical points and the endpoints. In your work, here are the things you absolutely need to show. You absolutely need to show the function that you're maximizing. You need to show that function of a single variable right here. I don't have to simplify it like this. It's really helpful too. You've got to show that the derivative is equal to 0 right here. And then you want to identify this guy as your critical point. The place where the derivative equals 0. Now having done that, we're going to evaluate our product P at all three, the critical point and the two endpoints. So, P of 0, P of 10, and P of 20. And I kind of like evaluating it in a factored form because it's easy. If y is 0, what is obviously my product? And if y is 20, what is obviously my product? 0. And if y is 10, what is my product? 100. And there's my max. Nope. Gotta say it right. There we go. Now we need to come back and answer the question, oh, I'm supposed to find two positive numbers. They didn't ask me for the product, they asked me for the two positive numbers. Have I found two positive numbers? Not yet. I found one.
Substitute.
And the other one's 20 minus 10, which is 10. Is it weird that my two positive numbers are the same number? No, that's fine. Does this make sense? Let's see, work it out.
How did you get 100
For P of 10? You can get it either in the factored form here, 10 times 10, or in the non-factored form, 200 minus 100. It's not P prime. Is that what you were looking at?
Oh,
Yeah. Classic mistake. Everybody does it at least once in their life. Don't feel bad, but it's a good object lesson. He took y equals 10 and he put it back into P prime. Shockingly, he got 0. Of course he would, because that's how we found 10 to begin with. We set the derivative equal to 0. What we're interested in is the value of P at 10, not P prime. Good, very good. Any other questions? Cool. Today, we're going to learn a very interesting theorem that is not commonly used by itself, but it's going to be the building block for tomorrow's theorem that is used all over the place. So think of this as a 2-day lesson. Today we're going to set the stage, and then tomorrow we're going to get to the main show. Today we're going to learn Rolle's theorem. And Rolle's theorem is a very sort of narrow and specific theorem that is going to guarantee the existence of a critical point for functions that meet certain conditions. If you think about the major theorems we've had so far, continuity guarantees intermediate values, right? If f is continuous on a to b, then f takes on all values between f of a and f of b. Continuity also guarantees extreme values. If f is continuous on a to b, then f has an absolute max and an absolute min on a to b. Now we wonder, what kinds of functions have to have critical points? See if you can draw yourself. In fact, let's do this. Let's draw a function that meets these conditions. It is continuous on a to b, and f of a equals f of b. Draw a function that meets those two conditions.
A, B, look what?
Wait, it always equals AB? I mean, it always equals FB?
F of A is equal to f of b. So you've got some interval, right? AB. And I want you to draw a function so that f is continuous and f of A equals f of b. It can do anything in between, as long as it's continuous. I see one? Yep, that's good. That works. Yeah. That's a sort of trivial example, right? Yeah, very good. I'm seeing some good functions here. Mm-hmm. Yeah. Okay. Still thinking of that. I might start by just picking a value for f of a and f of b, and as long as I'm curving between. So I'm going to start by choosing an a and b. Here's an a and b. What value do I want f of a and f of b to be equal to today? 6 works for me. So f of a and f of b are both going to be 6. And now I'm going to draw it so it's continuous in between.
That's not continuous.
Yes, it is.
Oh, never mind. Sorry, that's not
It's not differentiable, but it's continuous.
What does differentiable mean again?
It means that the derivative exists at every single point in the interval.
Can you, this is, I know this is confusing, but, can you remind me what base constant is?
Sure.
Is that like asymptotic?
When you graph.
Yes. So pause this right here. Su'a, we're going to go to a new page and talk about the difference between discontinuity and non-differentiability. Because this will be on your midterm for sure. So discontinuity is going to be any point where the graph jumps, essentially, or fails to be continuous.
Oh.
And so they come in 3 flavors. We have, what is this called? A point or a, what was the other term? Removable, right. That's the preferred term these days. Removable discontinuity. And we have, what's this called? Jump discontinuity. And we have our third and final one. What's this guy?
Asymptotic.
Asymptotic discontinuity. And if I give you a function in analytic form and say, where are my discontinuities and classify them, the tool of choice is the limit. Because what makes this discontinuity removable is that as x goes to c from both sides, f of x approaches L. But when I actually get to c, f of c is not L. Hence, I have right at that point a single discontinuity. So we would say that what defines the removable discontinuity is that the limit as x goes to c of f of x does not equal f of c. Okay. And what defines a jump discontinuity is that I'm cruising along coming towards C from the left here, and I get to C from the left, and boom, my function does something completely different from the right. And so we say that what defines the jump discontinuity is that the limit as x goes to C from the left is different from the limit as x goes to C from the right. It's all about the limit of the function. And then down here, what makes this asymptotic is that as I go in towards C, my function keeps on getting bigger and bigger and bigger, and what's our phrase? Without bound. In other words, f goes to infinity. And it may be plus infinity, or maybe minus infinity, it might be plus from one side, minus from the other side, whatever. By contrast, our types of non-differentiability are going to be places where I cannot draw a tangent line. Why might I not be able to draw a tangent line? Well, if my function is discontinuous, I can't draw a tangent line. So all of the discontinuities are also places of non-differentiability. I can't put a tangent line on that thing, or that thing. Certainly not that thing. Okay? So all discontinuities are also points of non-differentiability because differentiability implies continuity. Yeah. But also, there are several types of functions that are continuous but not differentiable, and they might have a feature such as a corner. Right here, where I cannot put a tangent line here because I have one type of rate of change from the left and a different type of rate of change from the right. Or a vertical tangent. And the vertical tangent is interesting because right at a vertical tangent, I can actually draw myself a tangent line. It only has one problem. Because it is vertical, what is its slope? It doesn't have one. Undefined slope. Specifically infinite. And then we also have the really strange one, the cusp.
The bird.
The herd, that's right. And a cusp has the feature that the tangent is vertical, but we have different signs of infinity on either side. And so what defines a corner is that the derivative from the right at C is different from the derivative from the left at C. Notice the big difference here. Here we're looking at f. Here we're looking at f prime. That makes all sorts of sense, right? Vertical tangent, f prime of c is infinity. Cusp. F prime of c from the left is negative infinity, but f prime of c from the right is positive infinity, or vice versa.
Wasn't there a fourth type that was also non-differentiable?
Well, all discontinuities will
Right.
not be differentiable. And then 1, 2, 3 in addition. And that's all that we say. There are other types of non-differentiability, but they're exotic. If you look at the curve f of x equals x sine 1 over x, it will be continuous at 0, and it will be infinitely wiggly around 0.
It'll be infinite.
Infinitely wiggly. The closer you get to 0, the more it wiggles. And so you can't draw a tangent line.
X. What was it?
X sine 1 over x. Make sure you're reading those. Yeah. Does that help?
Yeah, I remember now. Yeah, I just got mixed up.
Continuity is when f of x doesn't exist, and non-differentiability is when f prime of x doesn't exist.
Actually, f can exist. It just doesn't agree with the limit. So discontinuity is when f does not agree with its
So if
limit.
you filled in a little dot in the second one.
Right, then it would be continuous. But if I filled it in up here, well, if I filled it in the second one, there'd be a problem, because I've already got a filled in dot with arrow. So I can't have two different filled in dots on the same function in the same x. Because y values have to be unique. Okay, let's go back. Did all of you draw a continuous function so that f of a equals f of b? Does your function have a critical point?
Yeah.
Yes.
No.
Are you sure? Your function was a horizontal line, right?
So everything is.
You've got critical points all over the place, man. Every single value f prime of c is equal to 0. So, show of hands, how many of you have a function with a critical point? Yep, there it is. And so our goal today is really to prove that every single function that meets these two conditions has a critical point. And if I add the condition of differentiability, then I get something even stronger. I get a critical point where f prime of c is equal to 0. And that's going to be really useful. I'll say it, I'll write it, I'll prove
I
it.
have one, maybe I'm just not thinking of why couldn't it have. Why couldn't it have a critical point? Well, actually, no, it has to.
It does.
Yeah, never mind.
Yeah. Okay, so here is my claim. Here is Rolle's theorem. There are going to be three conditions we're going to put on f. If f of x is continuous, on the interval a to b, and now we're going to require that f be smooth. F prime of x exists, or another way of saying it is f is differentiable.
So yours would not apply.
Right, that's exactly right. Very good. And it turns out that I don't have to actually be differentiable at the endpoints. So we're going to relax that a little bit and say on the open interval a to b. So if those two conditions are met, and then finally, and if f of a is equal to f of b, if all three of these conditions are met, then there is a c in the interval a to b such that f prime of c is equal to 0. Rolle's theorem is a guarantee of horizontal tangents. Yes.
So when you wrote f prime of x, is this a b? Is that an interval or is it?
Yes. It's an interval. And let me draw a picture so you can see what I'm talking about. Any function that basically does this, a to b, and now draw a smooth curve between. No matter how I draw it, I'm guaranteed that somewhere in between, and maybe a couple of places in between, there's no guarantee that it's only one, there will be a horizontal tangent.
Is this saying just endpoints? Like, I know that necessarily is endpoints, but if it's not endpoints, if any 2 points equal each other, will there be a critical point?
That's a great question. So notice actually that I've got another place where these guys are equal, right? So what I could do if I wanted to, but I don't want to, is to actually just focus my attention right here. And now ask the question, does f of whatever b equal f of b? Yes. Is f continuous and differentiable in between? Yes. So do I have a horizontal tangent? Yes. Yep. So that would be like a subproperty. Now the proof is fun, because the proof allows us to use the theorems that we have had so far. So here we go. Proof. Let's see what we can figure out based on this. So let's see, f is continuous on a to b, on the closed interval a to b. So what do I know about f? It has to have what? True.
Extreme.
It has to have extrema. You're right. But also, important for our purposes, it has to have extrema because of the extreme value theorem. Since f is continuous, it's guaranteed to have an absolute max and an absolute min on the interval a to b. Since f is continuous on a to b, then f has an absolute max and an absolute min on a. So that's our first thing. That's the extreme value theorem doing work for us. Now let's have another theorem doing some work for us. We know that if x equals c, if f of c is an absolute max or an absolute min, then it can only occur at some specific points. Where do absolute maxes and mins occur? Critical points or endpoints. Exactly. Let's call the absolute max f of c, and let's call the absolute min f of d. So we'll have something. And so x equals c and x equals d must either be equal to a and b or be critical points. Because they are places, locations for absolute maxes and mins. Okay. Now we've got a couple of possibilities.
So the x does equal D or x does not equal D?
Does equal d. So what I'm saying is that since my max and my min are f of c and f of d, then the two locations from my max and my min have to either be at the endpoints or else they have to be at critical points. Okay? So let's take both possibilities. One possibility is that c and d are a and b. That's one possibility. And I'll just set b equal to d and a equal to c, and I could do it the other way and it would be the same thing. Well, if I do that, then now I've got a function whose max is f of a and whose min is f of b, and the max equals the min. How do you draw a function whose max equals its min? It has to be a horizontal line, that's right. So if a equals c and b equals d, that's one possibility. And that means that f max equals f min. Why? Because one of my conditions was that f of a had to equal f of b. So the only way to draw f is as a horizontal line. Well, if that's true, then any c in the interval a to b will satisfy f prime of c is equal to 0. Because the derivative of a horizontal line, badly drawn here. Let's try to move that horizontal line up before that. There we go. That's more horizontal. The derivative of any horizontal line is going to be 0 all along. So I just have to pick some point in here, right there, and f prime is equal to 0 at that point, and I'm done. But if not, then that means that either the max or the min occurs somewhere in the middle. Let me draw that. So let's say this is A, let's say this is B, and let's say that my max, maybe my max is right here, but my min happens somewhere in the middle. And let's call that point right there. If not, then either the max or the min occurs somewhere in A to B. And because the max or the min occurs somewhere in A to B, then that means that that point where the max or the min occurs is a critical point. Let's say it's the max. But if it's a critical point, then I know something about the derivative at that point. What is true about the derivative at critical points? 0 or does not exist. That's exactly right. So either f prime of c is equal to 0 or f prime of c does not exist. But I've already stipulated, and here's where I use my third condition, that f of x is differentiable on A to B. So that allows me to eliminate the possibility that f prime does not exist. And I conclude, therefore, that f prime of c has to exist. Since that's not possible, therefore, I conclude that f prime of c is equal to 0. Now, the wording for this proof is pretty long-winded. And you're seeing it for the first time, and you're probably going, huh. But let's actually go back over the concept for just a minute. And then, once we've done that, we'll do an example or two so you can see how this will work out. Here is our concept. What we're doing is what you guys all did. We're taking a function where f of a equals f of b, and we're drawing a smooth curve in between. And what I'm saying is that if we're drawing a smooth curve in between, I've only got two ways to draw it. If I go straight across, what's the derivative at every single point? 0. If I do not go straight across, I either have to go up or down, right? And if I go down, I'm going to have a minimum inside, and if I go up, I'm going to have a maximum inside. And if I go up and down, I'll have both. Well, every place where I have a minimum or a maximum, what does my derivative have to be? 0. Because it can't be non-existent. And that's it. That's the spirit of the proof. Does that make sense there, Ray? Okay. Yes. Now, let's actually use this. When we're using Raleigh's theorem, or any theorem, you first have to check the conditions. And then having checked the conditions, you can draw the conclusion. Alright? So here's how this would work out. Let's let f of x equal x squared on the interval -2 to 2. First question, does Raleigh's theorem apply to it? And second question, if so, find all c such that f prime of c is equal to 0. Now, one of the things that's a little bit of a pain about Raleigh's theorem is that it's got 3 separate conditions, and you have to remember them all. So let's see if we can remember them. What has to be true about my function? It has to be continuous on what?
A to B closed.
Closed. So I'm going to write that condition. Is my function continuous on my closed interval? Is this function continuous on -2 to 2?
Yes.
How do you know? You could draw it, but there's something about it that you know.
There's no closed and bounded.
What type of function is it?
Continuous.
Quadratic. It's quadratic. It's a polynomial.
Yes.
And we know that all polynomial functions are continuous. So yes. All right. Is it differentiable on, now here, I'm going to check just the open interval. If I can check the closed interval, that's okay, because the closed interval contains the open interval, but I don't have to have continuity at the end, the differentiability at the end.
What would an example be of a function?
I'll show you in this minute. Yep. Good, great question. So is this differentiable? To check that, I'm going to check the derivative. What is f prime of x? Does that exist? on every single x between -2 to 2? Yes. Okay. And what's my third condition for Raleigh's theorem? The one that makes the magic happen.
F of A equals F of B.
Yes, I have to check that f of -2 actually does equal f of 2. What is f of -2? 4. And what is f of 2? 4. Aha, my third condition is met. Given that all three conditions are met, I can conclude, therefore, there has to be a c somewhere between -2 to 2 so that f prime of c is equal to 0. How do I find it? It's really easy. I find f prime of c, which I've already done over here. F prime of c is equal to 2c, and I set it equal to 0, and I find the critical point, which lo and behold is right where the local minimum of x squared is.
And I think it's easier just to use the second rule first, like instead of using Raleigh's theorem. Like, you could.
Oh, in other words, could I just go straight for finding setting derivative equal to 0?
Yeah.
Yes. The point of this example was not that I needed Raleigh's theorem here to find this value. The point here is that I was guaranteed to be able to do it. If I changed my function so that the algebra was really hard, I would not necessarily be able to exhibit a 0, but Raleigh's theorem would still guarantee the existence of set 0. Does that make sense? Yes.
How does f prime c equal 0? Is that just known?
That is the conclusion that of Raleigh's theorem. If my function meets 1, 2, 3 conditions, then I am allowed to conclude that there has to be a horizontal tangent somewhere in the interior. Does that make sense? So Ben asked a really good question. Why couldn't I just set the derivative equal to 0 to begin with if I wanted to find it? In this case, I can't. But that's only because my function was really simple. Let's take a slightly more complicated function and see what I mean. Better make it... Yeah, actually that'll work. No. Okay, so here's a function. It's yucky. Now we ask a question. Does f of x have a horizontal tangent on the interval 0 to pi somewhere? Well, I tried Ben's method first. This is what we might call over the top. We'll compute f prime of c and set it equal to 0 and see what we find. And when we do, we get 2c, yeah. We get 2c minus pi plus cosine of c. We set that equal to 0 and we start to solve. And pretty quickly we start to cry. Because we can't solve this equation. So your direct method doesn't really help us. So now I say, wait a second, Raleigh guarantees me some horizontal tangents if my function meets some conditions. What are those conditions? Continuous, differentiable, and f of a equals f of b. All right, so let's check. Is my function, is f of x continuous on 0 to pi? And yes, because it's a polynomial plus a trig function, and the sums of continuous functions are continuous. Is it differentiable? Let me finish this real fast. On 0 to pi. Well, the derivative I've already found, and does that have any problem spots? You don't know. Yes. All right. Does f of 0 equal f of pi?
Yes.
F of 0 is 0, and f of pi is also 0. Check. So I am guaranteed a horizontal tangent even if I don't know where it is.
So you can just say yes?
So you can just say yes. There must be, we are guaranteed by